Well, 10 o'clock. Let's do it. Rob 101. 2nd of October. Hard to believe. We started end of August. It's just like a whirlwind to me. I don't know about you guys. So I'll get us back to where we were at the end of class on Wednesday. So we're talking about linear independence. We will be relating it to uniqueness of solutions to equations a little bit later today. So we introduced a notion that a set of vectors is linearly independent if and only if the only way you can add them up and get the zero vector is if you use the coefficients being all zero. So you can see that uniqueness is kind of baked in here. The only way to get this trivial solution is if all the coefficients are zero. And so that's the notion of linear independence. And so we did some examples by hand and saw like, wow, that's just no fun going through and checking all of those equations. So we had this pro tip. How do you do it in real life? So what you do, you stack up the columns into a matrix, and then those vectors are linearly independent if and only if the determinant of A transpose A is non-zero. And the way you check that is you write down an LU factorization of A transpose A. In principle, you may need to use the version with row permutations, but that's fine. And then, because determinant of P is never zero, the determinant of the product then is non-zero if and only if the determinant of the product of these terms is non-zero, but the determinant of L is always 1, and so it becomes if and only if the determinant of U is non-zero. And that's a much easier thing to check. We just look at the diagonal elements of U and make sure that it doesn't have any zero elements. Bingo. There's a zero element, the set is dependent, and there will exist a non-trivial solution to this equation. And if the U has only non-zero elements on its diagonal, the only solution will be the zero vector. And every once in a while, even I have to remind myself, what is the size of this vector? Where is it living in? And for us, it's the number of coefficients. Okay, so we're just getting set up to how you prove that pro tip when we left off. Okay, so we ended with this. We took a vector in Rn, has n components, and we said, yep, this vector is 0 if and only if when you square all of the entries in the vector and add them up, you get the 0 number. And that's because if this one is not 0, then this thing will be not 0, and etc. And then this sum of squared terms is actually y transpose times y. And that's going to be very useful to us, because if we just take this one times this one times this one times this one, we add them up, and bingo. So a vector is 0 if and only if vector y is 0 if and only if we do y transpose times y, and we get 0. And here I've carefully written down all the sizes. So what we're trying to do is we have this rectangular system of equations. We're trying to assert that the only solution to it is the 0 vector. And what we're claiming is that it's enough to look at this square system of equations. And when things are square, we know that all we need to do is look at the determinant to see if there is a unique solution or not. So that's the logic. How do we go from rectangular to square and claim that those two things are equivalent? So that's what I want to walk us through today, and fairly quickly, but all you are responsible for and being able to use in a quiz or something is this kind of result. You don't have to know the proof. But I think it's good to make sure that some of this stuff is not black magic. Okay, so this is what I'm going to do. I'm going to define y equals a times alpha. So that's a definition. And then I know y equals 0 if and only if y transpose y equals 0. That means I know a alpha is equal to the 0 vector if and only if, well, what is y transpose? When I transpose a product, I get the product of the transposes in reverse order. So this is alpha transpose A transpose, and then y is A alpha equals 0. So that's kind of the major, if you want to call it a trick, fine, but I don't think y equals 0 if and only if y transpose y equals 0 is really a trick. It's a simple fact. And then this is alpha transpose A times alpha. Okay, so are we done? The answer is no, but it kind of almost looks like we're done. We're trying to assert this rectangular system of equations has a unique solution, alpha equals 0, if and only if this thing does, okay, back and forth. But the thing is, we've got this extra, it's missing here. And that's a small detail, but it's really important. So how do we get that? How do we get that? Well, suppose A alpha is equal to 0. If something is 0 and I multiply it by anything over here, I'm going to get 0 again. Okay, so that implies that A transpose A alpha is equal to 0. And if this is 0, I can multiply by anything over here, and I'll still get 0 because I'll multiply both sides. That'll be 0 equals 0. Okay, and now I do my alpha transpose A alpha equals 0. But now look what I have here. Oops, this is supposed to have been implies. And illegible implies. Look what I have here. This guy equals 0 implies this one equals 0. That's from our little fact. So this implies A times alpha equals 0. Okay, I'll let you write that down. We'll take stock. But let's see what we've got. Let's call this A. Let's call this B. Let's call this C. And then this is just A again, okay? We have A implies B implies C implies A again. It goes all the way around in a circle. Each step is kind of trivial. You know, this is 0, I multiply on the left, it's 0, I multiply on the left, it's 0, and then I use this one little fact to get the equivalence of this to loop it back around. But that's the art of the proof, okay? Now, if I have A implies B implies C implies A again, what can I know, what do I know now about all the relationships between these propositions? It means they're all equivalent, because A implies B implies A. So A if and only if B. B implies C implies A implies B, etc. So we have, as a conclusion, A if and only if B, if and only if C. And for us, we only care about A alpha equals 0 is A, if and only if C holds, B holds, which is A transpose A alpha equals 0. That's the only part we care about. Whoops. Thought I had my block here. And then there's the pro tip. Once we have that, this is square, this is square, and so we have A alpha has only the trivial solution if and only if A transpose A alpha, I guess, equals 0, has only the trivial solution and then that's if and only if the determinant A transpose A is not equal to 0. Okay, so that's how the pro tip comes about. Question from the class, please.
How did you go from C implies to A, right?
C implies B?
A.
C implies A? Okay, so the question was, how do you get C implies A? Yep, so that's the question was, how do we get here C, A transpose, alpha transpose A alpha equals 0 implies A, which is this, okay? And so this was Y, and this was Y transpose Y. Up here, we just checked Y equals 0 if and only if Y transpose Y equals 0. And this is how I defined Y. So that's the key step in the proof in some sense, okay? So that was this one here. Y transpose Y equals 0 if and only if Y equals 0. And we defined Y to be A times alpha. That's A. And this is Y transpose Y. So, yep, this is Y equals 0. This is Y transpose Y equals 0. So that's how you get C implies A. Other questions? No, thanks for the question. Other questions? In the chat, maybe? No? Okay, so now when we want to check linear independence, we just throw the vectors in a matrix. This might have 13 rows, 5 columns, so it's 13 by 5. We form A transpose A, it's then 5 by 5, and we take its determinant. And the way we do determinants of high-dimensional matrices is we do the LU factorization, and then we only have to look at this term because it's the only possible term that can be 0. So that's the beauty of how all that fits together. Works? Okay, I'm going to put things in a little different order than I decided to do even 15 minutes ago, but let's look at uniqueness of solutions and relate it to this. Then we'll come back to another topic. Okay, so it's always a little stupid to change up in the middle of lecture, but hey, you know, I'm live and I'm risky. Are you guys alive and you're risky because you're in Rob 101? We know you're risk takers. Okay, so let's relate uniqueness of solutions to the columns of A being linearly independent. Let's see if we can figure out how that works, okay? How should that work? So A times X, we can write this as A1 column, A2 column, dot, 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 AM column. And then we write out the components of X, X1, X2, dot, 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 XM. Okay, and that's supposed to be equal to B. And so then what we really have here is X1, A1 column, X2, A2 column, dot, 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 XM, AM column equals B. Okay, so that's what it means. Whoops, didn't work. That's what it means for X to be a solution. So X is solution if and only if this holds, okay? So X's solution, just numbers, 13, 27, minus pi, divided by square root of 11, etc. They're just numbers. So how can we see that the columns of A being linearly independent is equivalent to uniqueness if there's a solution? So let's suppose we have two solutions. Let's call it candidate solutions. Okay. We'll call one X bar 1, X bar 2, X bar M. And then the dreaded X double bar. Two very ugly solutions. And the question when must we have X bar equals X double bar, which of course that's uniqueness. Okay, let me give you a chance to catch up with your writing. Let your brain calm down after all of the massive writing you've done. Okay, most of you have your pen down inside the class. I can't see what you have outside. So we're looking at AX equals B. and I'm looking at the columns of A, and then x1, xm are just coefficients, and so I have a linear combination of the columns equals a vector B. Now I take two possible solutions written in the most ugly fashion I could possibly have done. I don't know how I pulled that off. We called them x bar and x double bar. I want to know when is it obligatory that those two things are equal. So I calculated one solution, Tribby calculated another. Do they have to agree? That'll be uniqueness. Okay, so they're both solutions. Hence, a x bar equals b and a x double bar equals b. They're both solutions. Well, if I take a x bar and I subtract from it a x double bar, then that's b minus b, and that's equal to 0. And just to be clear, that's the 0, let's say in Rn minus 1, because A has n rows and m columns. Our typical A. Bingo. Okay, everybody agree? A x bar equals b, a x double bar, we subtract them, we get 0. Okay, so now that's 0, so that means a times x bar minus x double bar is equal to 0. Okay, but that simply means x bar 1 minus x double bar 1 times a1 column, x bar 2 minus x double bar 2 times a2 column, dot, 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 x m bar minus x m double bar, a m column gives me the 0 vector in Rn. Okay, so I just keep emphasizing that is not this scalar 0 in the reals, okay? It's the 0 vector. Okay. So what is the condition on the columns of A such that all of the coefficients in front of them have to be 0 and hence the solutions are the same? That's the definition of linear independence, okay? So you can see exactly what's going on. Okay, so alpha 1, A1 column, dot, 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 alpha m, AM column equals 0 is alpha 1 equals alpha 2 equals dot, 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 equals alpha m equals 0. That's equivalent to linear independence of the columns. Running out of space. Okay, so we can write that down as if AX equals B has a solution, it is unique if and only if columns of A are, not have, different verb, are linearly independent. So that's why we care about linear independence, and then we check it. Via determinant A transpose A not equal to 0. And then we do that by U has no 0 elements on the diagonal. And U comes from, whoops, not a derivative, P dot A transpose A equals LU. Our beautiful, whoops, LU factorization. Bingo. So uniqueness and linear independence, they go hand in hand. But that's the definition. So it was baked in to this, okay? Here's the columns of A. We can add them up. We get 0 uniquely if and only if these guys are linearly independent, forcing all of these coefficients to be 0. What we hadn't worked out was, where do those coefficients come from? And it is you take two different solutions. Yep, they have to satisfy the equation. And so you end up with A times X bar minus X double bar equals 0. And then you write that out, and the columns of A just pop out into your hand. And the coefficients are the differences between the two solutions. And if the columns are linearly independent, then this coefficient has to equal that coefficient, this coefficient, that coefficient, this coefficient, that coefficient in A. All the components have to be 0. And then we get uniqueness of our solution. Kind of amazing, huh? All that bookkeeping puts together, and you get this really clean characterization. And I invite you to go back to writing down x1 plus 7x3 plus 11x4 equals 5. Write all those out and figure that out from that form of equations, okay? You're just not going to do it. It's just not going to happen. So it's really nice to use the bookkeeping that matrices and vectors give us, and we can work out these pretty deep facts. Whoops, come on, scale back up. Fortunately, there's a return. Hit it again, yay. Okay. So questions on linear independence? Why don't you put them into the chat, and Trivia will let me know. We can have a quick pause and make sure linear independence is working for everybody, checking linear independence, and then how it relates to solutions of equations. I guess we're doing okay. Okay, here's kind of a gnarly question. Number of linearly independent vectors in a set. So if I give you, say, V1, V2, and our proverbial VM vectors in Rn, can we define the maximum number of linear independent vectors in the set? Okay, so that's the question. Why would we care to answer it? Whoops. And for us means it's important enough to spend time on it, okay? Okay, do you guys recall when does AX equal B have a solution? Okay, we had a condition involving the columns of A. Anybody remember offhand? I think you do, and you're playing hard to get today. That's if and only if B is a linear combination of the columns of A. Okay. Well, that means B is not linearly independent from the columns of A. So I can write B as a linear combination of the columns of A. Let you write that down, and we'll go back and just remind ourselves why that's true. Well, that was the definition of a solution, okay? You just write it down, and if you have a solution, it has to satisfy B as a linear combination of the columns of A, okay? So, okay, so that would mean if I, if I took A1 column, A2 column, dot, 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 AM column, and then I took a second set and I added B to it, that's still A1 column. Come on, write it out, Grizzle. You can do it. AM column, and I add B to it. These sets must have the same number of linearly independent vectors. Once you write out all the words you just said, the same number linearly independent vectors. Ugh, getting close to Halloween and I'm writing like it. Halloween font today. Okay, let's see what we got. AX equals B, so we need B as a linear combination of A. So that means I can build B from adding up these vectors. So if I'm looking at number of independent vectors, this isn't getting me an additional one. They have the same number of linearly independent vectors. So that's why if I want to test if AX equals B has a solution, I'm going to be comparing the number of linearly independent vectors when I take the columns of A and then I append to it B. I need the same number of linearly independent vectors. That's why that question is interesting. How many linearly independent vectors are there in a given set? If I can answer that question, I can test if adding B to it gives me another one. If it does, B is not a linear combination of the columns, and my equation does not have a solution. That's the implacable logic here. So that's how I will check if B is a linear combination of the columns of A. I will count independent vectors here. I will count independent vectors here. If they're the same, then B is a linear combination of these. I got nothing new. If it increases by one, B is not a linear combination of these. I have a new independent vector and I have no solution to my equation. Okay, so back to our vectors. How do we check the number of linearly independent vectors? So how to count number, oh, come on, write it out, number of linearly independent vectors in V1, V2, Vm. And then if we can do that, we'll apply it to columns of A and then columns of A plus B. And just check the number. That'll tell us if there's a solution or not. So that'll be cool. Just being able to count the number of linearly independent vectors. Well, how you do it, you just start from left to right. But if you want to work from right to left, it's fine too. Okay, so we'll start from left to right. Whoops. Oh, particularly challenging today. Do the following. Okay, so let's just consider the set consisting of the single vector V1. Is this linearly independent? What does that mean? It means alpha 1 V1 equals 0 if and only if alpha 1 equals 0. So I need your help. What's the condition on V1 such that the only solution to that equation is alpha 1 equals 0? Yeah, it was said lightly with a little bit of trepidation that maybe it's not quite right, but that's okay. I did the same thing when I would not even have said anything when I was a freshman, okay? I just sat there terrorized that the professor might ask me something. I know. It was said. That'll be true if and only if V1 is not equal to 0. And that is correct, okay? Totally correct, okay? So that's if and only if V1 is not the 0 vector. Okay, so let's just suppose that's true, okay? So suppose V1 is linearly independent. And just make a note, v1 is equal to the 0 vector, discard it, right? It's not helping you. But we'll discard one, a different one in a minute. Okay, next consider v1, v2, and ask if that's linearly independent. Okay, so now we got to solve the equation alpha 1 v1 plus alpha 2 v2 equals 0 if and only if alpha 1 equals 0, alpha 2 equals 0. Is that true? So we do the arithmetic. Let's suppose this time v2 is a linear combination of v1, okay? So if I could write v2 is some constant times v1, I would not. So we discard v2. Next. Well, we kept v1, we threw v3 away. We checked v1, v3 linearly independent. What do you want to suppose, yes or no? Let's suppose yes, so we get something more, okay? But it could be either way, so suppose yes. Next, you do v1, v3, v4 linearly independent. And I'll write etc. Okay, so it's totally doable. That's a U for super. But super tedious, okay? We would not want to do this for a set that had more than like 3 vectors in it. Bingo, save my work. I don't know why I'd want to save it, it's so ugly, but we're saving it. Okay, so. It's easier to see this way. We check v1 equal to 0, yes or no. Can I write v2 as a linear combination of v1? Let's say yes, we threw it away. We move on to the next vector. Is it a linear combination of now v1 or not? Let's say no, okay? Then we go to the next one. Can it be written as a linear combination of those? Yes or no? Throw it away, yes. Then we get all the way to the end. Is this vector a linear combination of the vectors that came before it or not? Okay, so that's how you would do it. Okay, so you can assign a number. Okay, so is there a better way to check this? Or a clean way to find this number that's equal number linearly independent vectors in a set. Okay, that's the question. That's the question. So we're going to skip the working out a particular example because I think you guys already get the idea that this is like super, super tedious. And so here's the SemiPro Tip. If there's time towards the end of Rob 101, we might upgrade to the professional version, okay? But this is for what we have now available to us. This is the SemiPro Tip. Okay, so T, F, A, E. Remember, the following are equivalent. That means one if and only if the other. Okay. So here's the first statement. The set of vectors V1, and I'm going to write them for a reason you guys already know, as if they were indexes into the columns of a matrix, because we love matrices. A12, A22, dot, 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 AN2. So these are my vectors in Rn. There's 30 of them, and they have 406 components. I don't care. It's all good for me, because I love Julia, okay? Whoops, I left out the name of that vector. It's VM. Dot, dot, dot. Okay, so there's our set of vectors. This set has k linearly independent vectors. In principle, found by working from the left and checking the process we just went through. The matrix A, so now I stack all these guys up. A11, A12, dot, 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 A1M, A21, A22, dot, 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 A2M, dot, 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 AN1, AN2, dot, 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 ANM. This matrix has k linearly independent columns. Okay, so that part is trivial because the vectors and the columns of A are the same thing. So we haven't really done anything worthwhile except we converted our vector problem into a matrix problem, and matrices are the bread and butter of Julia and all linear algebra computation packages. Next thing, we do an LU factorization of A transpose times A. Okay, so similar to checking linear independence, we're going to count this time. Okay. Then U has k linearly independent columns. There's an n in columns. Okay, so this is an improvement because U is upper triangular. Okay, so this is better for us. Because U is upper triangular. So it's much easier to check independence here and count vectors. Now, what you would love to do is not have to play with the columns of U. You'd like to just look at its diagonal and tell everything. That's what you want. And it's almost true, okay? Almost, okay. So we'll probably have to talk about this more on, okay, so that's the end of the equivalent, and then question. When can we look at the diagonal of U and simply count the number of non-zero elements? Ooh, that would be beautiful. Okay, so I'm 40 seconds over, and I'm pretty good about starting on time and ending on time. So we will pick up here on Monday after you've had a weekend to recover from working on your project. You've got your quiz due tomorrow evening, and no homework was due this week, so hope everybody has a great weekend, and we will wrap up chapter 7 early on Monday. Thank you.